right, now let's continue. Now let's do this way, that part. So the step number 1, when you go into the, usually when you come into this simulator, I think we can still try that. Let's wait until it, okay, now there's 2 ways to investigate this. When it comes to the simulator, now you remember all the functionalities, right? So in the middle, in the top of that right-hand side, it says the target. We're going to start with the sodium, and the show only highest energy electron, you can keep it click. If not, actually, it will show you other electron too. That's totally okay. And then these graphs are not really super important, but you can keep it click. And then you can see the vacuum tube and the 2 electrode, and the photocurrent shows here, and the battery will actually is the one we're using to apply the reverse voltage. Okay. Now when I switch on this one, intensity right here is at 0, but instead of intensity now, when I change this intensity, you can see intensity of the light changing, right? Instead of that, there's another option right here. If you click on the file option in the very top menu bar, it shows the photon comes in, and also it has option to do control photon number instead of intensity. So let's do that, I think, because the problem was that if I try to use the intensity and then control it, at any given moment, if I click the battery voltage, intensity is automatically changing inside the simulator. So that the way maybe they set up. So let's try with the photon. As I checked earlier, we can actually change that accordingly. Okay. So which means, let's say, for example, I want to try 20% of photons hitting. That means amount of photons emitting from this light at any selected wavelength, let's say 100, but right now it's emitting only 20% of that at a time. Okay. So let's do this with maybe a little bit of higher photocurrent, maybe somewhere in the middle of the UV region, like 240 nanometers. Now you can see the current we're detecting is about 0.770. That's a photocurrent. If I use the negative voltage here, let's try -1. If I use the -1, you can see photocurrent must be reduced, right? So that's what we try to understand. Whenever the photocurrent is 0, I have the stopping potential. So that potential is actually tells us the kinetic energy of the outgoing electron emitted from that surface. Okay, so that's the idea. Now this particle right here on the top coming from the light bulb is the photon, and the blue, this ball actually going between the electrode is actually the electron. Okay, now you can see amount of percentage is actually not changing. The problem earlier was that if that changing, I can't do this part of the experiment. Now all I have to do, change this number slowly. Make sure you're checking this percentage right here, because if that is starting to change, then it's not meaningful at all. Okay? Keep track on that, and the same time increase the voltage apply here, and then you can see when I reach about like 3 volt, current becomes 0. Now let's go back to 2. There's a current. Now I have to find exact moment when the current is 0. 2.5 is still current. 2.7 still current. 2.8 still there's current. 2.9 is 0, but let's try in between 2.8 and 9. How about 8.5, 0, 8.2, 0, 8.0? There's a number. So let's try with 8.1, 8.2. That's the exact moment, right? So now what we need is actually this percentage value right here should not change due to anything. Okay, that should remain in fixed. Now it's fine. Question. And then let's record. Okay, so now I think we can continue like that way. Stopping potential for sodium 20%, incoming photon intensity, reverse applied voltage 2.82. Let's continue to 50. 50% intensity, 2.82 till you have a small current. Let's try with 2.80, more current. Try with 2.9 is 0. So let's try with 2.83. Small number 2.84. Small number 2.85 is 0. Now you can see it changes, but very small amount. Okay, 2.85. And also make sure wavelength is changes little bit. Now I'm applying 240. Make sure you record that accordingly. We are on the high UV region, and the wavelength we apply in 240 nano, which technically doesn't matter those numbers because we're just doing this observation. Okay, let's try this 70% photon intensity. Now actually we're controlling number of photons emitting here. Okay, number of photons emitting. So let's try 2.85, already 0. We need to go back to 80 and then take a look where the exact 0 point happening. 2.80, I have a small current, 2.82, small current, 2.83, still small current, 2.84, small current, 2.85 is 0. So 2.85. Now you can see this, that's what we're trying to understand, whether this stopping potential is a function of incoming number of incoming photon or the photon intensity or not. If not, then technically we actually confirming the quantization of light. So the light energy is actually quantized into a frequency dependent frequency dependent item, not anything else. That's what it's actually confirming. Okay? Let's try 100%. Okay, still small current is there. So let's try with 6 is 0. So it almost like slightly changing from like 2.82 to 86. It's a second decimal place, but it may be at third decimal place, or maybe it's at fourth decimal place variation, because I can't see the exact decimal place between 85 and 86 because we don't have freedom of changing any other decimal place other than 2. So that's why we may see that is small different. Otherwise, it may not be a function of that voltage at all. Okay, voltage should be about the constant. That's all. It's a very simple observation. Question. Okay, so that's the important part is actually we have to select the option and then do number of photon instead of intensity there. Then it actually does what it's supposed to be. You can take a screenshot also. We need one screenshot. And then let's change sodium into zinc. And then let's do the same observation. Sodium into zinc. Let's try 20%. You can go backward if you want to, starting from 100%. Nothing wrong. I'm going to go back here all the way to the 0 and then start increasing slowly. Okay. And let's try -1. 1 is too high actually for zinc. Try with 0.5 there a little bit, 0.6, wall current 0.7 negative, 0. That means let's try 0.65 till the small current is there, 6.6 till there, 6.7 till there, 6.8 till there, 6.9 is 0. So 0.69. And then let's go back this into 0 and then let's change this number into 50%. Let's try again now. Current increases a little bit. Let's try -1, 0, so which means it should be less than 1. Let's try with 0.8, 0. Try 0.6, that's a number. Try 6.5, small value. 6.7, small value 6.8, small value there, photocurrent 6.9, till there, about 0.7, 7.1, 7.4, 7.5, 7.8, 7.9, 8, 8 is 0. That actually has a little bit of effect there, almost like 0.1 difference. So let me check very quickly, 20% again. 20%, I think the value we had is correct. 0.68 to 0.69 is the number for that one. That's okay. Let's continue. Let's try this with 70% incoming. Point -7, -8, 8.2 is 0. Let's try with 8.1. The 0.82. 0.82. So which means you can see after about like 50% in intensity, it actually remaining very consistently constant, but very lowest value is slightly off. I think it may be the measurement error, may not be the real any real meaning otherwise. Okay, let's try with 100%. 3 is 0.82. I have a little bit of number, right? So this should be then 0.83. So it's remaining consistent with our previous numbers, very, very slightly changing, but it almost not behaving any differently at all. Okay, so what it shows us, doesn't matter how much photon is hitting, the kinetic energy of the electron comes out is actually constant. So that's what it tells. So that's the idea of the idea proposed by the Einstein at that time. So if that is really quantized, the electron comes out, maximum electron energy coming out should be always remain in the constant. So that's what it actually shows. Question. Okay, let's take a look others. I can change the electrode into copper. We can do the same. We can start from 100%, go backward, or let's go back to 20. And then let's put the voltage 0 and then check again 20. It's a very small current. I will not need a lot of reverse voltage here. Negative, let's try 0.5. Already 0, let's try 0.2. Already 0.1. Value is there, maybe 0.15. About 1.4. 1.3. 1.2. That means about 1.2 and 1.3. It may be 0.13. Okay, let's put it voltage back into 0 and then let increase this into 50%. Now you can see that's where the change, a little bit of change actually happening when the intensity is above, number of photons hitting is about 50% or more. Amount of current it actually can emit remaining constant. But if it is less than that, it seems to be slightly changing, right? Up to 50%. That's what we actually see in here. Let's try the reverse voltage. Negative 0.5. Negative 0.3. If there's a number 3.3. It means 2. 3.3 is exactly when that happened. 0.33. Try 70%. 0.4 is 0, which means less than that. 0.35 still there. 3.6, 3.7, 3.7. 0.37. Let's try 100%. 38, 39, 4.40. Changes vary slightly on copper, but the sodium, it's very consistent because the sodium doesn't have a lot of free electron. Zinc also very consistent, but the copper is actually very good metal. So the copper has a lot of free electron. So the one reason maybe what we're observing might be that because of the free electron inside there may be chance of some electron actually bounce out. Let's take a look platinum then. Platinum should be much better metal than the copper. Go back this into 20%. Put voltage into 0 first to observe the current. Yeah, that's about the same number as the copper. You can see both of them are good metals. Try negative 0.2, already 0, 19, 18, 15, 12, 3. Yeah, it's 13. So it exactly behaves same as actually the copper, which means actually that is actually shows us how these elements behave or differ from each other depending on the intrinsic or the atomic nature of those elements. So these two are actually good metals, but these are not. Let's continue with percentage. 2 reverse, to 5 reverse voltage, to 7 reverse voltage, 3, 3, 5, maybe too high, 3, 4, 3, 3, 3, 2, I think it's 3, 3. 0.33. It matches exactly with the previous numbers which we got for the copper. Because both are, oh, I'm still on copper, I did not change it. We want to check the platinum, right? Let me change that. Let me check that again. Okay, I think I maybe forgot to change into platinum right here, the electron. Oh, I mistakenly re-clicked that. Make sure it's on platinum selection tool, otherwise the numbers is exactly the same. It might be because both of them are good metals, but I need to recheck that to confirm. Okay. 0 reverse voltage. Try negative 0.1. For platinum, actually, you can see there's no current emitting at all at this wavelength. So if I want to get the current, maybe I have to change the wavelength a little bit. So it seems to be no current at all. Let increase the wavelength a little bit and then see whether I can get the current. Platinum is actually a very good metal. So I have to go all the way to the very high UV region. Like earlier we were at 240, but I can't get any current with the 240. I may have to do about like maybe 182 nanometers. So then I can get the current. Let's do with that, okay? So these three, all the wavelengths are actually the same, this number, but maybe the other two I have to change it. So that's okay. So we can actually add that into here. Let's add one more column here. And then let's add wavelength of the applied EM wave for these three gonna remaining the same, but for the other may be changing, okay, because we can't see any current on that wavelength. That's okay. So the wavelength earlier we were using 240, I think. 240, 10 to the negative 9. You may have to add one line here and then add that information. Wavelength we're using 240 times 10 to the power minus 9, okay, meters. And these three maybe has to change. Now this one I'm using about 182. Let's take a look whether I can get the photocurrent with the same wavelength for all the rest of it. This one has about now 0.25. You may need to try to collect yourself, otherwise you're not going to really get the experience doing it. If you just get the data from a video, technically you're not going to get the experience what it's supposed to be, right? So it's a learning process, right? So that's the idea. Otherwise, I could do this asynchronously, right? I can record the video and then put it out. So the idea is that we try to do synchronously. That's why. Okay, that's a question which one of you asked. So that's okay, I think, to collect the data by looking at the video, but I would strongly suggest to do it yourself. Then only you can really get that idea. Okay. So copper is fine, I think. From the platinum, I need the different number, right? 182 times 10 to the power minus 9. Okay, up to copper, we are fine. Okay, let's try with platinum now. 20 percentage. I think it should be only very low voltage. Let's try with point, maybe 2 negative. Yeah, it should be about 0.12, 3.13, 14, 15, maybe 17, 19. 2. Okay, 0.2. So it's about the same like the copper, but it's slightly different now because I can't compare these two numbers exactly because the wavelengths are now slightly different. Okay, but you can see it's the behavior is almost, I think, the same because both of them are good metals. Okay, let's try now. Go back to 0 voltage, reverse potential. Let's try this 50 percentage. Try minus 0.3, 3, 4, 4 is 0. Maybe let's try like 3, 8, 3, 9 is 0, 0.39. It's, you can see its behavior is very similar, but we can't exactly compare because I may have to use exact wavelength for both if I want to compare, right? But this is just table 1 is just a observation. Okay? Table 2 is our main calculation. Let's continue this one. Let's try this with the 70 percentage. 70 percentage. 0.4, 5. So let's try for 4 reverse voltage. Let's try for 3, for 2. For 2, I have a small current. For 3, the current is 0. Okay. Yep. So we can do for 3, the behavior and the variation exactly same as the copper metal. Let's try 100 percentage. For 5 is 0. Let's try for 4 number. So the number is 4.45. So the variation is almost the same, little bit variation there. Let's try the calcium. Now, when it goes to the calcium and the sodium both are on the same column on periodic table, right? Because of that, you can see behavior for both of them going to be the same. So I can keep the same incoming photon wavelength, or I can actually change that wavelength into the previous one. Then I can compare with the potential right here. back potential for the sodium, but I think let's keep this number. That's okay. So let's try to stop this one. Try with large reverse potential, 8, too high, maybe 7, too high, 6, too high, 5, still too high, 4, 2, yeah. So for the sodium, it was like 2.82, right? So the calcium is in the same column, so it should behave about the same. But the wavelength is slightly different. We can't really compare, but it should be about the same. 5, 2.8, about 2.9, too low, 3, 3.5, about 4, 4 is too high, maybe about 3.9, 7, 3.8. In between 3.8 and 9, you should check like 3.85, 87, 88, 88 is the perfect number, 3.88. So I can't exactly compare those two because wavelength is slightly changed now between first three and the next two. Okay? So you have to be careful. Please add that extra column and then accordingly do that calculation. Okay. And that's all. So it's the same thing. You just increasing the intensity coming in and then checking the stopping potential. High with 4 reverse potential, too high, 3.9, too high, 88, too high, too low, 89, and 3.9 is the number. 3.9 variation you can see now almost negligible. 70 percentage, 3.95, almost 0, 90. There's a value 910, 3.91. You can see that variation between the voltage, reverse voltage, and the intensity is very similar to the variation we saw on the sodium because both of them are on the same column on the periodic table. And let's try with 100 percentage. 3.5 reverse, there's a number 3.8, 0.9, 95 is 0, 94, 93 is 0, 92, 0, 91 is 0. 9 you have a number, 91 is actually 0, 3.91. Okay, so that's the idea. So if I have the not very good metal, but there should be, the material should be have the last orbital. If you remember the chemistry classes, how the electron configuration for different elements. So the last orbital, if you have a non-filled last orbital, that electrons is actually not tightly bound. Those electrons can actually kick out from the orbit very easily. So if I have such a scenario, not the free electron, like a lot of free electron like the copper or platinum, those are not good. You can see photoelectron is actually very, very less, not good at all for this kind of application. But if I have a not really good metal, but an element which has actually last orbital, maybe 1 electron sitting there or 2 electrons sitting there, but can kick out easily, then this is actually very good for application. That actually will be observing here. Zinc, sodium and calcium is better. Zinc is not really good. It has a d electron orbital, is very heavy. Electron orbit is actually, the element is heavier itself, and the copper and platinum is heavier but has too many free electrons, which is not good, because if you try to kick out those things, actually the kinetic energy is going to vanish before even comes out the surface. So that will be a problem. All right, so That's all we can do on there with that observation. Let's start our main part of the experiment, that is actually calculating the Planck constant. Okay, that's the plan. Let's continue. Any question? Okay, then let's continue. In this case, we're going to do the same thing, but you can fix the intensity at some point and one particular number. We don't need to change the intensity all the time. Okay, let's keep it 100%. And then we will go back to the sodium, and we'll put 0 here. And for the wavelength selector, bring the wavelength selector all the way to the lowest possible the region, that is the highest UV energy we can get. Okay, now you can see it emitting a lot of electrons. You can see the number of electrons coming out from that surface is very high. Now what we're trying to do here, that is actually what the Einstein proposed. If the energy is quantized like we thinking earlier, then we should be able to detect that by external circuit. If we detect it as a function of frequency changes of the incident wave, then I can make a graph. Okay, by using the slope and intercept of the graph, we can maybe investigate Planck constant and the wave function and the work function. Okay? That's the plan. So let's go back here. Now we will try to do this all 6 different type of electrode, but sodium, I think definitely it's work, but the other things we have to check whether we can get actually enough data point to make the graph. Okay, we need at least 3 or 4 data points. Otherwise we can't make the graph. So we'll start with 100 nanometer wavelength in meters. 100 nanometer, I'm going to write this in scientific format. 100 times 10 to the power minus 9. But if you highlight this whole region, do that for both wavelength and frequency, and then right click, format cells, and then select the scientific with 2 decimal places. Scientific with 2 decimal places, and then in this number in front of that, put equal sign. When you're typing it, hit enter. Then that will automatically changes into the scientific format, what actually Excel reading. Okay. If you write it down anything scientifically on Excel, you have to write the number E, positive or negative, what's the power is. This is 100 nano, 100 times 10 to the negative 9. But it's writing, getting rid of that 2 zeros, 1.0 times e to the minus 7. It's the same number, okay? That's the wavelength, okay? I can calculate the frequency in the unit of hertz, 1 over second. Frequency gonna be now the speed of the light divided by the wavelength, right? Equal sign, speed of the light 2.99 times 10 to the power 8 divide by wavelength of the light is the cell you already wrote that answer, that is B19. Then it will do the calculation automatically. Okay. Let's add that function somewhere here. Frequency. Okay, question. Let's find this stopping potential for that one. That's going to be unit of volt. All we have to do, change the voltage, but with the negative sign. Let's try with a little bit larger value because current is much larger. -5, -8. -8 is the maximum number we can go, which means for sodium, I should not start at 100 nanometer because it's too high current. There's no way I can actually go more than -8. You can see still there's a current. I can't figure out it too much electron energy is too high. So what we should do instead, we can actually decrease the wavelength little bit. Let's go like maybe 150. Decrease like about maybe 50 below that maximum point. 135 even fine. Anything close to 150 is better, I think. Now I think definitely I can get a stopping potential. Let's try with -7. Yeah, now I can find the stopping potential. Okay. So which means the wavelength, I should not start with 100, we should start with 152. Anything close to 150 would be fine, I think. If you retype that number here, then that the calculation will do automatically. Okay? Let's check the stopping potential. -7, I think too high. Yeah, try -6, -5. Between -5 and 6, 5, 509 is 0, which means 58, 57, 585 is already 0, which means 583. There's a number 584. 585 is 0. Okay, so the stopping potential for the UV light with the the wavelength is about 152, is about 5.85. Okay. And now if I want to make that graph, I need at least 4 data points. That's why I have to start as highest as possible energy, which means lowest as possible wavelength. Then again, with our setup, we have a problem. I can't apply any reverse potential. These batteries allow us to change only up to 8 voltage. Okay, we can't change anything beyond that. So that's why we had to change the incident wavelength a little bit below the 100. I starting at 150. So I need at least 4 more data points. Let's try around like 200 now. Let's increase this close to 200. Any value close to 200. 202 is fine. Let's check the stopping potential. Maybe let's try with -2. -3 still there. -4. 0, which means try with -3.5, 3.8, 3.9 is 0, try with 3.85, 82 has a number, 83 is 0, 82 has a number, 83 is 0, right? So that means it's going to be 3.83. And then wavelength I'm doing 202, so which means equal 202 multiply 10 to the power -9. And you click and drag this one, it will do the calculation automatically for the frequency, because I have to make a plot frequency versus stopping potential. Okay, right? Then you continue, and I need at least, if I have 1 or 2 data points, that's good enough. We don't need really a lot of data points here. Let's try with 250. Close to that number. It doesn't matter what is the number is, something close to 250. Okay, let's try with -3 stopping potential, too high, -2. There's a number 2.5, 2.7 is 0, so which means 2.6 also 0, 2.5, 2.55, 58 is 0, 57, 0, 56. There's a number. 57 is 0, right? So which means you have to find as accurate as possible that stopping potential. Okay, 2.57, and the wavelength is, now we are applying 254 equal to 54 multiplied into the power minus 9. If you type that way, it will automatically change into the scientific notation, and this you can click and drag. Let's do at least 1 or 2 data points. Try anything close to 300. Seems to be 2.5 is much larger. Reverse potential 1.5. Try 1.7. 0.8 is too high, I think. 1.75. 1.77 is too high. How about 7.6? Has a number. 7.7 is 0. So the best zero potential we can get 1.77, and the wavelength is about now 3 or 4 multiplied by equal sign 3 or 4 multiplied by 10 to the power minus 9, and this you can click and drag. Let's try one more, and let's try 350, then it very close to visible region. 1.5 is already 0, maybe too high. 0.1, there's a number. 1.15, 17. Try with 1.16 is already 0. 15, there's a number. 1.16 is 0, right? So that's the best potential we can get, 1.16, and the wavelength 356. So equal sign 356 multiply 10 to the power minus 9. And you click and drag this one, then it will do the frequency automatically. Now, for the rest is also almost the same, right? All we're going to do, change the electrode material and then reinvestigate this one, right? But let's check with this calculation, because we want to make sure we can actually get the Planck constant by doing this. Okay, so let's first check that. To do that, I have to make a graph of frequency versus reverse potential applied, right? Let's check it out that first. Let's make a graph. Insert illustration pictures. No? That also we need actually earlier picture. So let me bring that too, because you need that for the procedure section. Let's include that also. So that is for the procedure section. Okay, let's keep that as our figure number 1. We can start naming the graphs from figure number 2. Okay, it's going to be then figure 1. Figure 1 just has to go to your procedure section, right? Simulator for photoelectric effect. Okay, let's insert a graph, scatter plot, and let's add the data, select, add. X-axis should be frequency values. Y-axis should be now potential values, right? Okay, click OK, click OK. Now you can see very nice smooth graph. So at least I think our expectation is better, but that now this number is very small value, right? But we try to calculate 10 to the negative 34. Any error happening in our potential, reverse potential, stopping potential measurement going to be very, very strong effect for the calculation. Okay, let's check it out, that one. So let's add all the axis title, primary, horizontal, vertical, and then the trend line, linear. Let's go to the trend line options. Let's do these two options. Don't put the intercept 0 because this one intercept is not 0. We should have a negative intercept, okay? If you want to check that, you can actually extrapolate this to the backward direction, and then you can check how this, where this line is actually crossing. So it should be this now, these two numbers, you can check that later, okay? You can change this number, forecast, backward and then reverse, backward and forward, and then change those two numbers. You can see this dotted line can increase downward and then it's going to cross somewhere here, which means it's going to cross the y-axis somewhere here below the 0. So the y-intercept is negative, okay? So numbers we have here, so we can use those two numbers to do the calculation. So let increase number of decimal places. Already we have about like 4 decimal places, I think. Let's check it out. That two number right here. Let's try maybe like 4 decimal places. Probably scientific. Yeah, scientific, but at least 3 or 4 decimal places. Okay, so you double click on this line right here around the equation, and then this icon right here on the very top, label options, category, scientific, number 3 on decimals. Then it will show you a little bit of decimal places there, okay? All right, now by using that, let's calculate. Slope is 4.156. If I go into the equation, slope multiplied by charge of the electron should be the Planck constant, right? Let's check it out, that one. On your table number 3, that's what we're doing. For sodium, slope is H over E. H over E, we have the value 4.156 e to the 15. 4.156 e to the power minus 15, right? So that's the number we have there. Yeah, so this also you have to change all of this into scientific, otherwise you will not get to see that the small numbers, okay? Highlight the whole area of the table 3, scientific, maybe 2 decimal places, because if you write it down with extremely small number, it should be on the scientific notation, okay? Now that is H over E. If I multiply that by E, I should get the Planck constant. Let's do that calculation. Equal sign H over E value, that's the slope of the graph, multiplied by charge of the electron 1.602 e to the power, or you can write just multiply 02 times 10 to the power minus 19, or you can type E minus 19. Either way is fine, okay? I'm getting 6.66 times 10 to the negative 34. So it's a very good number. I think if you go to your theory section, you have the expected value for the Planck constant. That is 6.626 10 to the power 34 negative. So we are in the very good margin of error. Let's do the PE. Equal sign ABS parentheses. That 10 to the 34 value cancels out, right? So I can compare that with this number itself, 6.626. 6.626, that's the expected value. Multiplied by 10 to the power negative 34 minus calculated value right here on this cell, that is F43, divide by parentheses 6.626 multiplied by 10 to the power minus 34, close brackets, multiplied by 100. So our number is about 4.8 times 10 to the negative 1, so which means the percentage error is about 0.48. So it's a very good number. So the experiment is fine. It works fine as we expected, but it's very sensitive data, okay? Because you can see the measured values are extremely small values, and then I have to measure that stopping potential as accurate as possible. If that is wrong, then this number going to be very incorrect. Okay. Question. Okay, unit right here, H over E. H is measured in terms of unit joule second. So you can write there joule second divide by the coulomb. Then you multiply that by again coulomb with the electron charge. Then you will get the right units what we expecting joule second. And let's check this with the y-intercept to get the work function. Y-intercept value right here, what we get 2.324 e to the 0, 2.324 e to the 0 in your graph right here, the intercept value. And to get the work function, I have to multiply that by again electron charge. Work function is actually negative right here, negative pi over E. That is the intercept. So if I multiply that intercept by the E, then I will get the work function. So let's multiply this number by E. Then you can find the work function for this one. Equal sign. This number multiplied by 1.602 times 10 to the power minus 19 electron charge. That's the work function. Question. Yeah, let's copy paste all of this function. You need the function for here, work function, this one. Just write it down here. Work function, and also you need the Planck constant calculation, this one, that is just H. And also the percentage error. Okay, so the work function I can't compare with anything. There may be standard values for each material, but I did not check that. So that's okay, because our main point of this whole analysis is to investigate the photoelectric equation and the concept, and then check whether we can get the Planck constant correctly. If we can get the Planck constant correctly, then we know all the concept behind that is actually correct. For example, the main concept what we interested is the quantization of energy. So that is correct. Okay. So that's what we try to check. I think it's fine. So everything worked nicely. So the only thing we have to do now, the work function over E should be joule per coulomb. And then if I multiply by coulomb, work function, you will get it just a joule, right? So that's what we actually observing here. So this value is incorrect, that function. I think let me do the calculation again. Intercept multiplied by 1.602 multiplied by 10 to the power minus 19. So it should be very small value in terms of energy joule. That's why I think earlier I mentioned that on Monday, generally if we're doing this kind of calculation, we would like to use electron volt energy. Electron volt mean compared to the electron charge, right? So if I divide this number by electron charge, electron volt is about 3.72. So that's why we're using that numbers. Otherwise, you can see these energy values extremely small values. Okay. So that's fine. I think all looks nice. So all we have to do change the electrode and then redo the experiment as much as possible. There's like 5 different electrode we can select. So we can take a look each one separately. Okay. So let's take a quick break and then we'll continue. Next is very simple. Now you know what to do exactly. In terms of graph, you can make a separate graph for each case, or you can put all the graphs in same graph. That is fine, I think. Doesn't matter. That we can take a look what is the best way. Okay, let's take a quick break. That. So let's take a look for sodium. I can try even the visible range. Now we are on the little bit high energy range, right, above the UV range. Let's try with the colors, like for example, violet, still fine, right? Apply this 0 here, just to check how much visible light can produce the, you can see the visible light current production is very small compared to the UV region, right? UV region, I have high current, but the visible, it's even at the violet region, that is the highest energy region in the UV. It's still a small current, 0.3. If I go to blue, extremely small. By the time we reach like green, that's it. So we can't get any current at all. You can see it. Maybe very little current, 5th or 6th decimal place, almost negligible, right? So that's a problem. So that's the main problem with this photoelectric materials, right? When you go to the lowest region, nothing there at all. Now, which means maybe as we go into the metals, probably we have to rely on just the UV region right here, okay? As highest energy as possible. Okay, now a couple of other things. Let's little bit edit this graph. So this is frequency, this is stopping potential versus frequency. This is for sodium, right? This is sodium, and the x-axis gonna be frequency. Unit's gonna be hertz. Hertz is 1/2 right? And y-axis is the stopping potential. Stopping potential unit is volt, right? All right, now since I have the one graph nicely organized and then everything there, then the later as we try to make the graph for different electrodes, all we need to do, we can put into the same graph sheet, or I can easily actually make a copy of this graph and then add the data. That the either way is fine, I think. We can try which way, both ways to check it out, which is the best way. Okay, so this is going to be then figure 2. This is stopping potential versus frequency for sodium. Okay, any question? Right, let's continue. All we have to do, all of these going to be the same, right? It's nothing different at all. It's the same thing. And all we're going to do, change the free wavelength and then check the potential, right? The stopping potential. Let's continue. And now to do that, let's change the medium into sync. And the highest wavelength, that's I'm getting the very good current, but the one thing earlier we came across is actually the stopping potential, because I can't use anything more than -8 here. You need to make sure by applying -8 whether this current can be 0 or not. If you can't, then I can't use that wavelength at all. Okay, maybe we have to start little bit above that 100. If I go into like maybe 100, even 110, I think it's fine. 100, 110, 115, no, 110, even 105, I think we are fine. Let us take this. Because if I can't get the 0 right here, then that will be a problem. Yeah, we'll start with 105. I think it's fine with 105. So you know this has to be right 105. Multiply by 10 to the power minus 9. Okay, it will change automatically into scientific format. Make sure all of these in scientific format. And this table, whole table, make sure in scientific format, the numbers we calculating extremely small values, okay? And I forgot earlier, each calculated the Planck constant unit should be joule second, and the PE doesn't have any unit, it's a percentage value. You can put percentage sign here, but even without that, it's okay because there's no particular unit for that. That's fine. Let's continue. Now for this one at 105 UV region, let's take a look what's the best. 7.8 even 0. What about 7? We have a number. 7.5 is 0. 7.2, 3, 4, 4.5, 4.7, 4.9, 4.9, then 50. 50 is 0, yeah. So 7.50 is the stopping potential for 105, and the frequency, you know, you have to multiply this number with the speed of the light, equal sign 2.99 10 to the power positive 8 multiplied by the wavelength, that is the cell value E19, okay? Cell value E19, then you will get the frequency. And this should be in scientific format. Let me take a look at that number. Very small value, should not be that. I think, yeah, you need to make sure in scientific format. No, still not correct. It's -7. Oh, divide by, that's fine. Okay. All right, it should be on the order of e to the power positive 15. Okay, so make sure you check that the frequency. And I think I wrote it down earlier. The command we use, the speed of the light divide by the wavelength. Okay, that's important. Check that out. Right, all looks good. Then let's continue the same way. Like you can decrease this by about like 50 nanometer, maybe like 152, and then check how much reverse potential we need to stop the current. About -5, too high, I think. -2, too low. -4 is too high. -3, maybe 3.5. 3.8. 3.9 is too high, maybe 8.5. 8.3, maybe 8.4. 8.5. So the 3.85. 3.85 stopping potential, and the frequency, the wavelength we're using 152, equal 152 multiplied 10 to the power -9, and the frequency you can click and drag this. We'll do the calculation, and the order should be 10 to the power should be about like 15 when it is around 100, 152, and then when it cross 200, it should be maybe going into 10 to the 14 level. Okay, check that. That's important. And then you continue likewise. Then let's go into like about 200, 199, and then try to find the potential. -2 seems to be too high. -1 too low. 1.5, 0.7, 1.9, 5, 9.3, 9.1. I think it should be 1.92. That's the best we can get, 1.92. And the wavelength is 199. 199 multiplied by 10 to the power -9. Make sure you put the equal sign in front, then it will automatically convert into scientific notation. Okay, and click and drag. Let's do maybe 250. You may not need to get exactly 250, anything close to that, okay? Because I try to get like 5 data points each like 50 nanometer increment. Okay, that's what I'm doing by keeping the UV region. Okay, 248. Check this with the 1 volt. It's already maybe what our limits 0 volt. We have a current. Let's try with -5, -0.5. Still there's a current. 0.7 is 0, which means 5.6, 5, 6, 7, 6 is 0, 6, 5. We have a number. So the best we can get 0.66 of current, 0.66 of reverse potential, and the wavelength is 248 multiplied by 10 to the power minus 9. Frequency, click and drag. And let's try one more data point. Let's try around like 300. Anything close to 300. And you need to make sure when the battery voltage is 0, there should be a current, otherwise we can't do that number. You can see now when the battery voltage is 0, there's no current at all, which means with the sink visible region, it will not produce any current at all. So that's the idea. Sink is not good element to apply for photo cells at all, right? So that's why these elements are not good anyway. So that's why these days it actually people trying to figure out is actually compound. Okay, but we can get one more data point like between 248 and 300. We can try maybe like 280. Let's try 280. Or maybe like 270. Anything greater than 248. I think 284 is still not enough current to measure. How about 270? Yeah, 265 we can still get a current. Small, but that's good enough. Minus 0.5, minus 0.4, 0.3, 0.2. There's a number 0.25, 0.27, 0.28, 0.29, 0.30, 0.30. Reverse potential 0.30. Wavelength is 265 equal sign 265 multiply by 10 to the power minus 9, and then this one you can click and drag. Now to do the graph, now it's the same calculation. Rest is right here. It's just very simple. Same calculation. I just need to make the graph. So to make the graph, the best way is that you can add the graph right here. So to add the graph, you need to double click here in the graph sheet. Select data. You have to rename the previous one. You can actually rename the series one. You can click edit. Series one name should be now sodium, right? So I'm going to name it because otherwise I don't know which one is which, sodium. And then let's add a new series. So the name going to be sync for that one. And the X values, again, the frequency values. Now it should be on this part right here, okay? F 19 to 23, and the Y value should be the new stopping potential. So that is G 19 to 23. Click OK, click OK again. Now you will see the new data set with the different color, okay? Then you can identify which graph is which. Keep this data right here, and also you can actually double click, go into the chart elements on your left hand side, then you can do the legend. If you do legend, I'm going to do the legend on the top, then you can identify which is which, okay? So that's important. And then I need to have a new trend line linear for the sync, okay? And then double click on that, and then trend line options, click last two. Intercept, do not click that, okay? All right, so make sure if you're adding more and more data point, that graph should be make sure a little bit larger, then we can see it clearly. Okay. All right. So that looks good. And the intercept is, again, I have to put the decimal places correctly. If you double click on that box around the equation, then the new window will appear. Category general, select the scientific, number of decimal places at least 3. Then you will get more decimal places in that equation values. Okay, slope is 4.177. Slope is 4 equal sign 4.177 multiply by 10 to the power minus 15. Should be 10 to the power minus 15, and the slope is 4.381. The intercept is 4.381. Okay, slope is 4.177, intercept is 4.381. 4.381. And this you can click and drag because it will do the calculation automatically. One thing to keep looking is the H, okay, Planck constant. So it's still good, very nice value, close to the expected number, and the percentage error less than 1, okay. So that part is simple. Then let's do the another electrode. So it's the same thing now. The rest is there's no difference at all. So we actually collecting or investigating the different electrode. Okay, now you know the process, you just need to continue. Okay, ask me any question if you have. Okay, so let's change the electrode. Now you can see sync, the visible, even the visible highest doesn't meaningful at all. Current is almost 0. Let's try the copper. Now, if I have a copper, you can see visible region doesn't produce any current at all, even the highest visible, because it's a very good metal. It is not really good at all to apply this kind of application. But for the UV highest region, maybe we can able to get some current here. So I'm getting good current there, but before we proceed with the 100 nanometer, make sure you apply the highest possible voltage reverse, and then make sure you can get the current. If you can do that, then we can start from that point. Okay. So let's start with the same units and everything, nothing changes here. Only we changing is the medium. Now the medium is copper. Wavelength we do in 100 nano equals sign 100 multiplied by 10 to the power minus 9. Make sure you change these into scientific notation, format, scientific with the 2 decimal places. Okay, these two also, frequency and wavelength, format, scientific, 2 decimal places. And let's check the potential now. Reverse potential, let's try with -7. There's a value. Let's try 7.5. 7.8 is 0, which means 7.6. There's a number. 7.7 is 0. Let's try 6.5. Number 6.7. 6.9. 7.7 is 0, right? So this potential should be 7.7. Frequency equals sign, speed of the light 2.99, 10 to the power positive 8, divide by the wavelength. Wavelength is on the cell value B26. That should be about 10 to the 15, on the order of 10 to the 15 positive, okay, frequency. Then you continue, and also the copper, I don't think we can go all the way very lower values of UV either. It might not produce any measurable current. We need to check that before we proceed. You can see even at 295, there's no current. And we can try 270, no current, like 230. We have a current there, maybe like 250 we can get a current. Anything above 250 there's not meaningful. Okay, I have to get 5 data points in between 100 and 250. Okay, let's try 100 and let's try 130. 130. Make sure current is different too with this point and the next wavelength. If not, then that also not good. So we have to have a different current between those 2 points. 100 and 100, maybe 46, 6.7, which means the potential will be different now. Let's try with -7, -6, -5, -4, -3. There's a number, which means let's try 3.5, 0.6, 8, 7, 7.5, 7.7, 7.9, about 7.8. As a current 7.9, 3.79 reverse potential, and the wavelength 146 nano. Okay, equal 146 multiplied by 10 to the power -9. The frequency you can click and drag, and then you continue. Now I can't go 50 at a time, right? I have to maybe do a little bit differently this one. So if I do 50 at a time, that may not be a good idea. We can go maybe like 40 or 30 at a time. Okay, maybe let's do, earlier we done 146, we can do 166. Try with 166 or 170, 177. -3, too high, I think. -2, good. 2.5 high. 2.3 high. 2.2, there's a number. 2.25. 2.7. 2.9. 2.3 is the best reverse potential. 2.3. And the wavelength is 177, equal 177 multiplied 10 to the power -9. And then frequency you can click and drag. Let's do 2 more data points. We can go all the way to 250 is the highest you saw earlier. Let's try around like 200. Check the current, it should be a different number. As far as it is a different number from previous, we are fine. We can try even 190. Let's try like about 196. -2 reverse potential, already too high. -1, let's try 1.5 reverse potential, 1.6, 1.7, which means let's try 1.65. Too high, I think. 2, 0, 1. Yep, 1.61. 1.61 reverse potential. The wavelength is 190, equal sign 196 times 10 to the power -9. And then frequency you can click and drag. Okay, so let's do one more data point for that one. Put back the voltage into 0. Reverse voltage. Let's try 100, 220. High with -1, already too high. So which means how about -0.5. -0.5. 0.7. 0.8. 0.9, too high, I think. Let's try 0.85. 6. 8.7. 8.8. 8.8. So that's the best value we can get, 0.88. And the wavelength is now 221 times 10 to the power -9. And the frequency you can click and drag. It's good. So let's add that data also into the same graph. So then maybe we can do two graphs. Each graph has like three lines. Okay, so that may be better. If you put all 6 into one graph, it might not be a good idea. So let's do like two graphs. Each has like 3 lines. Double click on the graph sheet, select data. We're going to add a new, not edit, add. Next series is copper. And X value is going to be frequency value C 26 through 30. Y value is going to be potential D 26 through 30. So that goes very close to the previous data points. Okay. Right here, you can see it extremely close by previous data set. And that's okay. Just add the chart element, trend line linear for the copper. Double click on the copper line, trend line, show equation and the R values. So this is actually for copper. This number is actually for this orange line. Okay, so you may have to put that numbers as close as possible to that line. Then the later, if it is needed to identify, then you know how to identify. Okay. Or what you can do is actually you can put the colors into this equation. Is that possible to put the colors actually in that equation? So right here, you can find the text color somewhere, and then you can use different colors. The colors appear for the dot, same color, put it into this equation. Then you can identify which is which equation. Otherwise, place that equation as close as possible to the line. Okay. Now this line should be for this one. Double click. Let's change that category into scientific around 3 decimal places. Okay. So, all right. So the slope is 4.162, equal sign 4.162, multiply 10 to the power minus 15, and intercept is about 4.740. Intercept is 4.740. These you can click and drag. It's I think it's still good. Yeah. So it's about the same number we're getting. So our error is very, very small, and the work function you can see changes. And also you can see work function for zinc and copper is actually very closer, but the sodium is very different. Okay. That actually decide the amount of energy comes out. So if the work function is better or the higher, then you can see the removing the electron is actually difficult. If the work function is lower, then the removing the electron is easy, then you don't need a lot of energy comes in with the light. Okay, so that's the idea. That's why for the sodium, we can get photoelectrons with the visible region all the way even down to like green color. But for zinc and copper, we can't observe that. Okay, only UV region can emit that. So, question? All right, then let's continue. It's the same thing now. I think you can do it yourself, but let us continue next tree also. So it's not a big deal. We're just going to change this into platinum and then repeat the same process. Okay. Before you do anything, make sure you check this. Put the potential into 0 and then check whether you can actually observe all of the photocurrent at a range of wavelength or not. Okay, if you can't observe the range of wavelength, then that is not good idea, right? So that's important. So in this case, let us take a look at the lowest for the platinum. Yeah, good. And the UV region, how high we can go. If I go to the visible, definitely there's no photocurrent, right? Because this metal has a very high work function. And if you go down a little bit for the UV region, very low energy UV region, even like 250, nothing emitting. 220, nothing emitting, maybe like 196, 182. That's the only region I can get. That range of current is extremely small. You can see almost like negligible, right? So I think we should not maybe do platinum at all. Let's try calcium and unknown. So the platinum energy is extremely small, okay? So let us skip the platinum at all. So let's try calcium and unknown. So let us skip that part. I think it's the same thing, nothing much to learn from there in terms of new, nothing new there. Let's try calcium, definitely will give us a better electron flow. And the unknown, I don't know which one is that, but I think that will give us a better numbers too. Let's try calcium. Calcium is fine. Even at the visible range, it has a nice electrons emission. Yeah, down to the little bit of violet region. That's good. Let's go to the highest 100. We'll start from there. Okay. Any question? I skipped the copper. It seems to be not much meaningful. And then if you do like sodium, zinc, and calcium and unknown, that's good enough, 4 of them. But since we done the copper, include that too. Okay, we already completed that. Let's check whether I can get this into 0 with the 8. Not possible. Like we had the issue with the sodium. Maybe we have to start like 150. If I do that, we can stop that with the enough reverse potential. 6, 5 reverse potential, too high, 5.5. It's too high, 5.4, 4.5, too high, 4.4, 4.3, 4.2, 4.1 is a number, then the 4.2 is the best, right? So the reverse potential 5.42 and the wavelength we apply now 149. That scenario is very similar to the previous one, sodium, okay? 149 times 10 to the power minus 9. And then you continue, frequency is equal sine 2.99, divide 2.99 times 10 to the power 8, divide by the wavelength. Wavelength is cell number B33. And this should be on scientific notation, highlight format cell, scientific with the 2 decimal place. Okay, these also highlight format cells, scientific with 2 decimal places. And then likewise, we'll continue. Right, so let's bring this like 50 nanometers higher, like about like 200. Try with negative 3, 3.5. Too high, 3.3, 3.35, too high, 3.4, 3.3, 3.2, 3.33. So it behaves very similar to the sodium scenario. Okay? 3.33. Wavelength is 199 times 10 to the power minus 9. Frequency you can click and drag. And the wavelength, let's increase by around another 50 or so. 240, 2.5 reverse voltage, too high, I think 2.2, 2.25, 2.7, too high, 2.26, 2.25. There's a number 2.26, it's 0, 2.26. Wavelength is equal sine 240 multiplied by 10 to the power minus 9. Once let's click and drag. And the next wavelength, let's go around like 280. Try this with the -1 reverse potential, 1.5. 1.5 reverse potential, I think too high already, 1.3, 1.4, 4.5, already too high, 4.4, 4.5, 1.45, 1.45. Wavelength is equal sign to 84 multiplied 10 to the power minus 9. Frequency you can click and drag. Wavelength, let's do like 300, maybe 20 or so, probably, right? Yeah, there's enough current. Let's try with negative 0.5, negative 0.7, negative 0.9, 98, I think too high, 97, too high, 96, too high, 95, 94, 92, try with negative 0.8. There's a number, 85, 87, 89, and 0.9, maybe 91. Yeah, 91. 0.91, and the wavelength is 323 multiplied by equal sign 323 multiplied by 10 to the power minus 9, and then click and drag. And then the process is same. You have to make the graph, put the intercept and the wavelength here, and then do the rest of the calculation. Okay, I'm going to get rid of the platinum one here because it seems to be current is too low, photocurrent, almost impossible to do. Let's collect the data set first for the unknown, then put the data into the graph in a bit. Okay. This one also you need to check the range first. Equal sign seems to be, I can go maybe UV region lowest, probably we can go around 300. So we should start the lowest possible and then make sure I can have enough reverse potential. Otherwise we can't start that number either. Maybe we should start at 130. Let's start at 130. Equal sign 130 multiplied by 10 to the power minus 9. Reverse potential for that, negative 7, try negative 5. 5.9 is too high, maybe 5.85 is also too high. 5.8, there's a number. 5.84, 83, 82, 5.83 is the best value we can get. 5.83 reverse potential, frequency you know equal 2.99, 10 to the power 8, divide by the wavelength. Wavelength is on cell number E33. E33, that should be on e to the power positive around 15 range in the beginning, low wavelength region. Okay. Then you increase this about like to maybe 177 or like 30, 40 at a time. Try with negative 4, negative 2, maybe too low, negative 3, probably a good number, 3.5, too high, 3.2, 3.3, too high, 3.25, 27, 29, 3.3 is the best. 3.3 wavelength is equal sign 177 multiplied by 10 to the power minus 9. Frequency you can click and drag. And then let's collect a few more data points for that one. Let's do like maybe like 210, 215. I think that's okay. Let's try with negative 2. 2.5, too high. 2.1 is also too high. Maybe I should try with 1.9 then. 1.9, 2.0, 2.1 is 0. Maybe I should try 2.05. There's a number 07, 06 is also 0. Yep, so we should do 2.06. That's the best value. 2.06. And the wavelength is 215. 215 multiplied into the power minus 9. Frequency you can click and drag. Let's do only 2 more data points to go. Let's do like maybe 250. -1, 1.5, already too high, 1.3, 1.1, 1.2, 0.25, 27, 29, 28, 27. We have a current. 28, current is 0, 1.28. And the wavelength is 248, equal to 48 multiplied by 10 to the power minus 9. 10 to the power minus 9. Frequency you can click and drag. Let's do one more data point, like maybe 284, close to 300, about 0.5, no current, about 0. There's a current, about 0.2, 0.3, -0.3, maybe 3.5, -0.4, -0.5, too high, -0.45, 47, 49, 48, -4.47. There's a current. -0.48 is 0. That's the best value. 0.48. And the wavelength equal to 93 times 10 to the power minus 9. So that's good. So that two data set. So we have a few more minutes. We can still, I think, check out those numbers. So we are doing calcium and unknown. So we can put it into the same graph, or the best way is that let's make a copy of this graph right here, because it's going to be too much otherwise. So let's make a copy of that graph and then make a secondary graph for last two data sets. Okay. So this is going to be now, first one going to be, you don't need to say for sodium because it's for many, so you can leave it like that, the term. So all the additional information on actually right here inside the graph. Okay. And the graph right here, sodium on the top also you have to get rid of, because that's not meaningful. We have more than one data set in the same graph. Okay. So let's get rid of that. Let's get rid of this right here also. And then let's add new data. To do that, let's double click on here, select data, and then delete one of them, remove one of them. Other two will edit. Okay. So edit, sodium, you have to say now new one is copper, series name copper. X values, delete anything there, and the X values for the copper should be frequency C 33 true 37, and then Y values D 33 true 37. Click OK, click OK again. So now the blue one is copper. Let's edit the other one also, the orange one. Double click, select data, click on the sync, edit. Now there's no sync there, new one is unknown. We can actually identify the material if I know the wave function, if I have the data set, right? So delete the X values, frequency for that, and delete the Y values, potential for that, reverse potential, click OK. Click OK again. Now that is actually for unknown. Now you can see the everything automatically edit, right? The legends and everything. So this is the figure tree. And all I need now is the slope and the intercept. You can see the slope is about the same, but the intercept has to change because that's the work function. Work function depending on the material. Okay, for calcium, slope is 4.169 equal 4.169 multiplied by 10 to the power minus 15. And the intercept is about 2.94. 2.94. And then these you can actually click and drag, but we're not doing the calculation for the platinum. Okay, we skip that because platinum is almost current is extremely small, no meaning actually measuring that. You can see my Planck constant, that's a number you need to take a look, that is fine. Okay, and work function you can see now very different than any of the previous. Unknown slope is 4.173, 4.173 multiply 10 to the power minus 15. Oops, why the negative sign is there? This short 10 to the power minus 15, okay. And the intercept 3.758, 3.7758. You can click and drag this, it will do the calculation automatically. The Planck constant and the error for that you can see very nice. And the work function you can see now 6.0. It does not match with any of the previous numbers, right? It may be matching with a little bit more towards the more metallic region, but if we without having the data table, I can't really identify that material. Like if I have the data table which shows all the work functions, then I can use this to identify that material. Okay? Like the density measurement, you can identify the material, and then heat capacity measurement, we identify the materials. So the same way, actually, this experiment too, I can even identify the material if I know the work function already done for that. Okay. All right. Any question? Okay, so I would think that is fine. So I would think this is okay to keep the, make sure these lines are not crossing with these numbers, and the legends should be visible because we have more than one line in the same graph. Make sure you have that, and make sure you edit these topics accordingly, then the name accordingly for the graphs, because now I have more than one line for each graph. Okay, I can't say which is which unless if I showing the colors and the legends there. Okay, so I think we can stop here. So if you have any question, stay on the call. Otherwise, the next week is the exam. Okay, next Monday we will be doing the exam number 3. If you have any question regarding the exam, always reach out. And otherwise, I will see you guys next Monday then.
Professor, for table 1, how did you adjust the simulation to compensate for sodium and platinum being having extremely low stopping potentials?
Say it again.
Right. In terms of table 1, how did you adjust the simulation to compensate